Good afternoon. Today I'm going to talk about my research on photochemical generation and oxidation kinetic studies of chromium 5-oxysalin intermediates. I'll talk about the background and significance of this research and then quickly move on to the results and discussion. And then I'll conclude by talking about the outcomes as well as possible future studies. So numerous transition metal catalysts have been synthesized to mimic the active site of cytochrome P450 enzymes. These enzymes are important for the oxidative transformation of molecules in our body. They're responsible for the metabolism of toxins as well as prescription drugs and the synthesis of some hormones. So shown here is a metalloporphyrin, which mimics the active site of those P450 enzymes, and it consists of this porphyrin ring with transition metals in the middle of it. Now, several reactions can be carried out using metalloporphyrins, including hydroxylation, epoxidation, and sulfoxidation. In a similar vein, we can use metallosalins, which have similar structural and catalytic properties to metalloporphyrins. And most importantly, we can modify the ligand surrounding the metal to generate asymmetric environments. Now, these asymmetric environments are important because they allow us to control the chirality of our oxidized products. In general, oxidation reactions are important in the manufacturing of pharmaceuticals as well as fine chemicals. It can be used to mitigate pollution as well as generate new forms of energy. Now, the purpose of our research is to understand the structure as well as the nature of these high-valent metal oxide species involved in these reactions. So in terms of the mechanism of salen chromium catalyzed reactions, it involves an oxygen atom transfer process, where this oxyligand can transfer to organic substrates. However, these active oxidants are very short-lived and they're difficult to detect and monitor. Most of our knowledge is based upon the isolation characterization of a single salen chromium 5 oxide species. But in general, there's limited evidence for the existence of most of these salen metal oxides. So previously, our research group has developed these visible light-induced ligand cleavage reactions, which basically involves the homolytic cleavage of this oxygen-halogen bond in this apical position, which induces a single electron oxidation of this metal, or it can involve the heterolytic cleavage of this oxygen-halogen bond to generate a two electron oxidation. And we were able to do this with several different porphyrin models as well as corral models. There's several advantages to this photochemical method. First off, there's a greater temporal resolution and also allows for us to do direct studies of oxidation reactions in real time. Another thing is that the kinetics are not convoluted. So in chemical methods, we typically use an oxidant to generate these active intermediates, which could convolute our kinetic measurements. And also, these reactions are environmentally sustainable. So shown here is the light-induced formation of that cationic chromium 5 species. So we take chromium 3 salen chloride, react it with silver chlorate or bromate, inducing a ligand exchange reaction. And then in the presence of visible light, we can induce heterolytic cleavage of this oxygen-halogen bond to generate that chromium 5 species. And we looked at two different ligands here. So here are the UV visible spectras for 1A, 2A, and 3A. So if you look here, 1A corresponds to this chromium 3 salen chloride complex. It has a distinct peak at 422 nanometers. And upon reacting it with silver chloride or bromate, we get a blue shift to about 410 nanometers. And then in the presence of visible light, we can generate 3A, which has this broad peak from about 550 nanometers all the way to 800 nanometers. We also use electron spray ionization mass spectrometry to characterize this complex 3A here, and it had a mass to charge ratio of 612. In addition, we can use chemical methods to generate this species 3A. So we take our complex 1A, we react it with 2.5 equivalents of purity of iodobenzene diacetate, which is a mild oxidant, and we get this spectra here. So 3A has this very broad peak, but it's not very distinct. So we added the donor ligand pyridine and oxide, about 10 equivalents, to make it more defined. And if you look here, we can see a very distinct peak at 680 nanometers. So with these photogenerated and chemically generated intermediates, we then reacted them with excess amounts of organic substrate. So shown here is the decay of 3A with cyclohexene, about 0.15 molar, over the span of 10 minutes. And when we monitored the decay of the 680 nanometer peak, we saw that these rates fit to a single exponential decay under pseudo first order conditions. Now, when we obtained the kinetic plot by plotting these observed rate constants versus the various concentrations of cyclohexene, and we obtained this very linear regression here. And from this linear regression, we obtained a second order rate constant of 8.7 times 10 to the negative third inverse molar per second. This is important because we also use the chemical method with cyclohexene, and we obtained the exact same second order rate constant. So this shows that these two methods are kinetically indistinguishable. So moving on, we also obtained second order rate constants for these activated hydrocarbons as well as these substituted thioanesols. And the most important thing to note here is that 3A showed much lower second order rate constants, and that's because we have these bulky tert-butyl groups on the 3 and 5 position of this aromatic ring. And this basically hampers the reactivity of the complex. However, if you look at 3B, we have no steric congestion here. Another thing to note is that with these substituted sulfides, in general, they had much lower second order rate constants, which was unexpected because this chromium 5 salen oxide species is actually very electrophilic. So it would undergo nucleophilic attack of these sulfides very readily. However, we rationalize these results by suggesting that maybe these sulfides are coordinating to these to this complex here, and thus preventing its reactivity. Another thing to note is that with parafluorosulfide, we saw a much higher second order rate constant compared to the other thioanesols here. We also looked at the catalytic oxidation of sulfides using these chromium salen complexes, and we obtained near quantitative conversion of sulfide to sulfoxide. And also we had relatively good chemoselectivity. So shown here, this corresponds to the sulfoxide, while this corresponds to the overoxidized product sulfone, which has 2 oxygens on the sulfur atom. One thing to note is that with 3B, we saw a decrease in the chemoselectivity, and in the presence of purity and oxide, we didn't see much of an improvement in terms of selectivity. We also noticed that with these para-substituted, with the para-substitute on the aryl ring, it's had a massive effect on the general reactivity of these complexes towards the sulfides. So if you look here, we can see that these parachloro and parafluoro substituents here are more electron demanding. So they decrease the reactivity of our salen complexes. However, with these more electron donating sulfides, we saw an increase in reactivity. So shown here is a Hammett correlation plot. It has the logarithm of the relative rate constant of the substituted thioanesol divided by the relative rate constant of the unsubstituted thioanesol here. And this sigma constant corresponds to basically the strength of the polar character on these substituents. And we got this nice linear regression. And from the slope, we got a rho value of negative 2.73. And this value corresponds to basically the reaction sensitivity to these various substituents. So there was so this in general is very sensitive to this reaction. The most important thing to take away from this, that this information suggests that there's a development of a positive charge at the reaction center during the rate limiting step. Shown here are the relative rate constants, and if you look, we can see that these rates were very different, which suggests that during under catalytic turnover conditions, we are generating a more reactive chromium salen species. And this suggests that maybe the mechanism behind sulfoxidation is different for what's going on with the activated hydrocarbons. In terms of outcomes, this is a novel and easy photochemical method, and it's indistinguishable from the chemical method involving iodobenzene diacetate in terms of its spectroscopic as well as kinetic properties. We rationalized the photochemistry here with the heterolytic cleavage of that oxygen-halogen bond, resulting in a 2-electron oxidation of the chromium metal. Based on the catalytic sulfide oxidations, it suggests that there is a more active chromium intermediate. However, we need to develop more methods to detect as well as characterize this elusive intermediate. In terms of future studies, we plan on looking at analogous metal oxosalin complexes, including manganese 5 oxosalin. I'd like to thank my research advisor, Dr. Zhang, as well as my lab mates, the Department of Chemistry, the National Science Foundation, and the Graduate School, as well as the Office of Research and Creative Activity. Thank you.